Hi, I'm Kurt Reinhardt. I am the Director of Information Engineering at Section, and I would like to talk to you this morning about what Section has been doing and what we think about when it comes to deploying workload at the edge, operating at the edge, and how to reap the benefits of operating at the edge. So, as with the conference in general, we're focused on sustainability, wanting to see how we can reap those energetic benefits at the edge and as we move from cloud to the edge. And we really operate at trying to understand the efficiencies and how to access those efficiencies. And we see a key piece of that as being a context-aware, location-optimized workload scheduler, which I will explain to you. So, as many of us know, data centers, they started out as on-premises facilities. They were often, energy efficiency was often the least concern. It's more important to have high uptime, have maximum power available, that sort of thing. As many of these functions started to be taken over by large cloud providers, there's now a business incentive to increasing the energy efficiency of these locations. And so even as we have seen more and more workload move onto cloud data centers, we have actually seen a flattening of the increase of the energy consumption. So they're able to achieve some of that energy efficiency in the way that they're managing those data centers. Now we're moving into a new era of the edge. We have a lot of new facilities that are being built using state-of-the-art technology, which is further increasing our energy efficiency. Smaller locations don't need the same climate controls and systems of that nature, and so that's reducing the energy footprint of these particular ones. So we like the idea of being in there, but they are small and there are lots of them. And that presents challenges for human engineers to be able to actually figure out how, where, when to deploy systems into these edge networks in order to support our sensor networks, our users, our app, whatever that workload may be. The edge does present challenges as well as those benefits. One of the ways that we look at it, Section 2, is, and I hate to contribute to confusing technology or terminology here, but the edge can be thought of as a static micro data center locations. The edge can also be wherever we can get the compute out closest to where it needs to be used. And that need and that use is the key piece to that, because that's not always static. In most cases, it actually is dynamic. You think of a mobile, widely distributed network like vehicle fleet operations, where we can have sensor networks, we can have inferencing models on board those vehicles, but they still need to be connected back to something else in most cases. There's typically still data transfer for model updating, information sharing, operations and maintenance of the systems. And so that requires some way to be able to stay connected to these mobile, widely distributed networks. Another case of a dynamic edge situation is a sporting or a cultural event, a big music concert or the Super Bowl, something of that nature, where the day before there's nothing going on in that location. Next day, there are tens of thousands of people there. And then again, on the third day, there's nobody there anymore. So there was a point in time when that localized spot, which, stadiums now are going to have these 5G facilities built into them, and they're going to have opportunity to host edge compute there. They will be running it, but you don't want to be running it there on a Wednesday, right? You just want to be running it at the football game on a Sunday. And so that implies a dynamic workload schedule, because always on deployments are going to be cost prohibitive. You could say, well, at least I'm always on in the edge, and that has a better energetic footprint. than being always on in the cloud. And that could be true. The cost to you may be prohibitive. And even though it's got a better energy signature, why would you want to be deployed at the football stadium on a Wednesday when there's nothing happening there, right? So the ideal is to be there when you need it. And that's why you can actually get in there from a business standpoint. It's going to be more efficient cost-wise. You can take advantage of the energy efficiency of that edge, but you're not necessarily paying for it when you don't need it. And so this is what we mean by this big mouthful: context-aware, location-optimized dynamic scheduling. So context-aware, what's happening? Location-optimized, where is it happening? Dynamic scheduling, time to put the workload there, and then when it's done, time to pull that workload back. So edge and cloud have a similar profile in this very simple view. This simple view is the trade-off between the cost and the benefits, right? The cost and the performance. That performance can be energy efficiency, it can be compute efficiency, it can be latency to end user sensor network. And there is some point along that line that my business is comfortable being. You know, my particular application use case fits. It's a utility curve from economics, and it's basically saying, this is the level of cost I can bear, and this is a level of performance that I'm happy with, and so this is the place for me to be on the curve. Now, somebody can come in, give you a bunch of extra money, and you can say, sweet, I'm going to pour that money into moving us up that curve. We're going to move along that curve, and we're going to get to a higher performance point, but we're going to pay for it. With an adaptive edge scheduling system, you have the opportunity to actually shift that curve, not just move along it by paying more or less or accepting more or less performance, but actually shift what's possible for the dollars that you have. You can, instead of being deployed off and on in a cloud data center, you can now be deployed off and on in an edge data center, a micro data center. And so for the same cost, you could get improved sustainability performance, better energy efficiency. But in order to manage that cost, you're going to have to be there very specifically when you're needed, and then you're going to have to leave otherwise, because otherwise that's going to ruin your cost profile here. So by shifting the curve, you can get the same performance at a lower cost, or you can get better cost, or at the same cost, you can get better performance. I think you understand what I mean there. So that's what we're talking about when we talk about dynamic scheduling in this context. And so we came up with a simple demonstration, and the simple demonstration is really contrasting a static deployment with a dynamic deployment. We have some terms in here like cloud and that sort of thing. And I don't want to confuse this as a comparison between cloud and edge. I think everyone here understands the benefits of the edge. The point we're trying to make is about static networks versus dynamic networks. So we built two apps. We deployed one statically. We stuck it in a cloud data center, and that's just where it lived. We took another one and the identical app, a copy of it, and we deployed it dynamically on the Section platform, which has a component called the Adaptive Edge Engine, which does exactly what we're talking about here. So that's the workload. Then we created a series of test agents, and these agents are servers that are going to be passing data, in this case HTTP requests, back to these apps in order to simulate our end user network. So that can be, again, customers on mobile devices, it could be sensors on vehicles, you name it. So these test agents are sending HTTP traffic to the apps. And each test agent is in a particular location. We have test agents in Asia, in Europe, and in North America. And in each of those places, their traffic is going to follow what would be a typical daily pattern for HTTP request traffic. It's moderate during the day, it peaks at night, and it falls off. It peaks in the evening, then it falls off at night when most people go to sleep and actually set their devices down. So we have in Asia, for example, test agents. One of them is sending this daily pattern of traffic to the static deployment The other one is sending the exact same pattern of traffic to the dynamic deployment. And so we just ran them, and we ran them through a few of these daily cycles, and we just tracked the performance. In this case, we were just looking at latency um, as our proxy for compute performance. But again, I think you understand that we can think more broadly about what performance means. And actually, this engine has an optimizer in there, and we can tell it what we want the objective and the constraints to be. We can say that the objective should maximize energy efficiency, and it can make choices based on that. But in this simple case, we went with latency. And this is an illustration of the dynamic deployment, and it's sped up quite a bit. But what we're seeing here is we have a map, and on the surface of that map are the locations of our test agents. And those test agents are communicating with the app, and the app is deployed in regional data centers, which are illustrated by those glowing blocks in the middle of the image. And then the beams of light, that's the actual data transfer. That's the communication between these two things, HTTP responses in this case. So as we're watching this, we can see that the intensity of traffic ebbs and flows from each of the locations on the Earth. And that's simulating real cycles of activity in our distributed networks. Now, we can also see an ebb and flow in the regional data centers. We can see them communicating with the test agents, and then when the test agent traffic diminishes to a certain level, which is configurable, then that regional data center stops serving traffic, and that's when they wink out and they become transparent. So this is a real-time illustration of the dynamic scheduling that we're talking about. This is the dynamic version of the app. The app is actually being copied and moved around to where it needs to be. Now, again, we're using cloud data centers, but this is going to be exceedingly powerful in terms of edge data centers, where you can get right at the exact point you need to be for the time you need to be there, and then pull out and move to the next best place, right? And this is a very simple summary of the latency statistics from latency measurements from the tests that we ran. So we have these two box and whisker plots. The upper one is from the dynamic deployment, which is illustrated here as section edge. And then the bottom was that static deployment that was in a single cloud data center. And not surprisingly, the latency distribution is much tighter and has a lower median in the dynamic section edge case. That stands to reason. It was running in a variety of locations such that it could minimize the latency. It was intentionally trying to be as close to the traffic as it could be. Whereas the static deployment was just where it was. It was just where somebody decided to put it at the time. And this gets to one of the real benefits of having a system that can be automated to optimize your preferences without needing an engineer to stand there and have to look at the data, cross-reference this and that, make this decision, and then actually choose that thing and then go out and manually deploy it in that other location. That's always been a bottleneck to really being able to unleash the power of the edge, is we have these systems which have yet to emerge to be able to capture the real dynamic opportunities here. And that's exactly what we've been working on, because we think that to realize the value of edge compute, we need to have a new operating system for edge compute. We need a new way to be able to make these connections and seek the ultimate goals that we have around performance, around profitability, around sustainability. So in summary, there are very real benefits to the edge. And energy consumption, efficiency, sustainability is one piece of that. Compute performance is obviously another piece. And in a lot of ways, these two things go hand in hand. What stands in the way is the cost. The edge comes at a cost. If we're having to rent space in other people's infrastructure, if we're trying to build our own infrastructure, you name it, there just will be a cost associated with it. It may not be growing at 4x as some people project and that sort of thing, but there will be some efficiencies there. But in the end, it still comes down to making sure that we can afford to be where we need to be when we need to be there. So even in IoT networks often are going to have some type of backhaul network that has to run across the internet. And so they can have, for all their forward-looking and edge-leaning capability, they can have some very traditional deployment concerns underpinning them and backing them up. And so whether those, in some cases, may be on-prem, and they can be quite energy efficient, or a cloud is even suitable, can be energy efficient, there's still the reckoning that needs to happen with the dynamic nature of this and how to be able to meet the needs of dynamic deployment so that we can realize all of these values, so that we can bring them together, make those trade-offs intentionally, and then be able to go out and actually act on those in an effective way. And so a dynamic adaptive approach to managing the networks is going to offer financial and energetic benefits by bringing the edge, dynamism, the ephemeral mobile nature of edge compute to all levels of the network. So again, my name's Kurt Reinhardt. I work at Section, and I really appreciate you watching this talk today. We're very excited about the opportunities to the edge. We're very excited to be one of the many companies who are contributing to developing it, making it accessible, and making it powerful for everyone. And again, thank you for coming, and I hope you enjoy the conference.